Hi everyone, thank you for coming to my talk today. I'm Eugene Lim, also known as Space Raccoon Online, and today's talk is titled, All Your Database Are Belong to Us, Getting Started in Vulnerability Research with Code Execution Bugs in Office Applications. In the past week, you might have heard about CVE 2021-40444, a Microsoft Office remote code execution vulnerability via the MS-HTML browser rendering engine. This is one example of how Office applications can be a potent source of vulnerabilities due to their wide usage. For this talk, I will share a small slice of how my team got started in vulnerability research and hopefully help some newcomers in starting their own VR journey. So first, who am I? I'm a cybersecurity specialist focusing on vulnerability research and application security at GovTech Singapore's cybersecurity group, which helps protect citizen data and secure government digital assets. Online, I go by the handle Space Raccoon, and I blog at spaceraccoon.dev, as well as tweet on SpaceRaccoonSec. I've been on HackerOne for about more than 2 years now, and I've hacked on a variety of programs from mobile to web to even some native. However, I've never really touched vulnerability research, and I've always been curious about this field, so I decided to get started sometime in the middle of this year. So why do vulnerability research? In fact, the term vulnerability research is quite wide, and there are a lot of different interpretations of what it means. Our resident meme lord on Twitter, Pom, actually has a pretty good analogy where bug hunters are cooks and security researchers are chefs. So, a cook is someone who has a good mastery of basic techniques, follows the recipes, but a chef takes cooking to a new level by finding new ideas, creating new combinations, and in much the same way, vulnerability researchers actually focus on products and find 0 days or new vulnerability techniques among them. So this actually takes you to the next level and adds a big punch to your current arsenal of offensive security techniques. So vulnerability research, or VR for short, is the process of discovering and exploiting new vulnerabilities in products. And it covers many different domains, such as reverse engineering, code review, dynamic and static analysis, and fuzzing. And it combines all of these so that researchers are able to discover novel bugs in both white box or black box products that they are looking at. So while there's some overlap with typical pen testing, VR actually requires new skills, some that you saw earlier, such as reverse engineering, but also some that I haven't mentioned before, such as memory corruption, exploit development, and debugging. And coming from a web security or application security background like me, this was actually pretty daunting, but it was also a new opportunity to learn additional skills in cybersecurity that I might never know where I might use them, and also is actually crucial to doing well in VR. You can't just use the same old techniques that you have from AppSec or WebSec. You do have to pick up some of these very critical skills in order to do well in VR. As I mentioned, it can actually be pretty scary to get started in VR because, at least from an outsider's perspective, VR looks extremely impressive but also very complex, especially with the kind of high-profile targets that VR researchers will kind of target, such as Microsoft Office or Adobe Reader. So a lot of these products that are used by many people all over the world and actually require a bit more in-depth research in order to exploit. And one of the pieces of advice I got early on was to get started by focusing on a specific file format. For example, there are pretty good examples such as the ACE file format that allowed Checkpoint Research to find a code execution bug in WinRAR, or maybe even the MDB format, which is a kind of database format, through the Microsoft Jet Engine, which is a very well-researched piece of software. And of course, you might have more client-side facing stuff like font file formats that was done by Star Labs. And the reason for this is that file formats is one of the most common entry points into applications. Most applications have file processing or file parsing functionality, and this allows you to cast your net wide rather than focusing on a specific application and what the application might do. You can really just test this out across many different applications and not get stuck on one, because if you get stuck on an application that's really well secured, that might be very discouraging for you as a beginner vulnerability researcher. So this also has an advantage because it helps you get started with fuzzing as well. Fuzzing tends to be based on file formats, and this is, I think, a better way or faster way of doing things rather than maybe doing pure reverse engineering. Or, if you're not the kind of person who likes code review, then you don't really have to get that deep into it. You can really start with fuzzing or gain a broad spectrum of skills to get started as well. Based on this strategy, I found the DBase database file format, a legacy format still in use by many applications today. DBase has a pretty interesting history. It first started out as a kind of IDE for developers to build their own programs and thus use a DBase database file format for data storage. However, the DBF file format has gone on to many different users, from spreadsheets in Microsoft Office Excel and Apache OpenOffice to the shapefile format, which is actually a collection of 3 different file formats, including DBF, that is used in geospatial data applications such as ArcGIS. It's also, of course, used in different databases as a form of an on-file database, and is accessible by different database engines such as MariaDB and Microsoft Jet Engine. So DBF is actually used by a variety of applications and does have this legacy file format history, which makes it a bit more interesting, especially for vulnerability researchers who might be looking for lack of security or considerations of memory corruption issues in these file formats. DBF came out in the 1980s, in 1983 to be exact, and it's almost 30 years old. And it first started out as a kind of a proprietary format without RFC, or request for comment document, which kind of lays out a lot of these specifications from different file formats. However, even without the RFC, it is still well documented, especially by DBase itself, which is the successor to the DBase company, as well as other independent websites such as independentsoftware.com, as well as the Library of Congress, which does very well to document the various versions and extensions to the DBF file format. So what we see here is kind of the header of the DBF file format, and it starts, of course, with the version byte. So the different versions of DBF actually exists with different support for data types. And then you have the date of the last update for the database, the number of records in the table, the number of bytes in the header, and the number of bytes in the record itself. And then there are a few more reserved bytes that have various users depending on the version. And then there are a few descriptors. And this is kind of the most important part of the format because it describes the different fields in each record, or you can think of them as kind of the columns in a spreadsheet. It defines them in the data type, such as it could be a character, it could be a long, it could be an integer, it could be a date, different file formats, data types, and also the kind of the field length of each field. So how many bytes you can expect in each field. So this has various implications on how the data is structured and how programs are going to parse a DBF file, which gives us kind of a ripe environment for fuzzing for vulnerabilities. Based on these various documentation, I could construct a fuzzing template for GitLab's Peach Fuzzer. And I've written about this before on my blog. You can refer to the link for more information. But Peach Fuzzer is basically a format-based fuzzer that takes in these templates that define the kind of data structure that they're going to be fuzzing, and it does various mutations based on the data types and the structure of the data that you feed it. So I built this fuzzing template, wrote it for the DBF file format, and then used it to fuzz various DBF file, small file applications, such as a DBF viewer, a DBF view. There are many of these tiny applications just scattered across the web, written by different developers, whose only purpose is really just to open a DBF file. So I don't start at the most complex applications. I start at really simple, small applications that are easy to fuzz, especially by Peach Fuzzer, which is what someone considers a dumb fuzzer. It opens the entire executable. It doesn't really use a harness. It doesn't really do coverage guided fuzzing. It just uses the application, opens the file based on what your mutations you've created, and hope it crashes. And as you can see in the screenshot on the right, we were actually pretty successful at getting a lot of crashes because many of these applications were written years ago, or they might not be well maintained, and thus they have a lot of these vulnerabilities. So this gives us kind of an insight into some of the common weaknesses that programs that open DBF files might have, which will be a clue for us later on when we go deeper with more complex applications. Now, when you get all these crashes with Peach Fuzzer, it's not actually a 100% positive sign that it is an exploitable crash. So it's really important to have some kind of triage mechanism on the back end to make it easier for you to find out whether something is exploitable or not. And one of the useful features of Peach Fuzzer is that it automatically runs the WinDBG Bang exploitable extension in order to triage these crashes. So what we see here on the right is what it is found is that at the time of the crash, based on the stack, there was an exception handler chain corruption. And this is, if you're kind of familiar with the basics of memory corruption, this is one of the most commonly exploitable vulnerabilities. It's really easy to exploit it. And it's also one of the most obvious signs that the stack has truly been corrupted. So it's rightly triaged this as exploitable, which allows me to quickly just zoom into these kinds of crashes and analyze them instead of wasting my time with less exploitable vulnerabilities. Once I've selected the crash that I'm interested in, I can actually refer to more of Peach Fuzzer's logs, which tells you what kind of mutations it carried out on the original file to create that crashing file. And based on that, I open it up in a software called 010 Editor. It's a hex editor with a special function that allows you to use templates that kind of tells you exactly which bytes in the file correspond to which fields in the file format structure. So that's kind of the bottom half of the screen you see here is telling you which fields are being highlighted in the top half, which is the actual file itself. And based on this, I slowly start removing big chunks of bytes from the original file while ensuring that it continues to cause the same crash. This allows me to quickly kind of whittle down the bytes that are not relevant to the crash at all, slowly move it down into something called a minimal viable crash. And that's the file on the right that you see here. And I've cut it down from more than maybe like 18,000 bytes to just less than 200. And the important thing here is that this allows me to perform really pinpoint the root cause analysis, the exact byte that caused the crash. And we're going to talk about this in the next slide. Now that I've created the minimal viable crash, I could inspect the byte that was changed by Peach Fuzzer that caused the crash. And based on the template that I used in 010 Editor, I found that this was actually the field type byte that determines the data type of a certain field in each row. And this time, the field type had been changed from an integer, which is marked by the I character, into a short integer type column, which is marked by the 2 character, ASCII character. And what this means, from my reasoning, was that this told the software to allocate a 2-byte buffer to support the short integer type. And at the same time, it was also copying for each row the number of bytes into that 2-byte buffer. But instead of using the file type, data type, which was 2 bytes, it actually trusted another field in the DBF file format, which is called field length. And this also tells the program how long they should expect that data type to be. But even though the data type is 2 bytes, the field length itself was much larger than 2 bytes, and this caused a mem copy of a buffer size field length into the 2-byte buffer. So now if you think about it, if field length is maybe like 100 instead of 2, the program is going to try to copy memory of 100 bytes into a 2-byte buffer. And this is not going to be enough. It's going to cause a buffer overflow, which leads to our crash. Using this buffer overflow, I could then override the structured exception handler and thus jump to my own shellcode and execute my own arbitrary commands. So what you see here is an example of this type of exploit on Scalabium DBase Viewer version 2.6. So first, using this application, I'm going to actually open my payload DBF file, which has been edited to run the memory corruption. And after corrupting the memory, it's going to jump to its own shellcode, which actually just pops calculator. So this is a very simple, straightforward exploit. And the reason for this is that a lot of these smaller DBF file format parsers are actually not compiled with any kind of memory protections. And thus, it's a pretty straightforward exploit. Now that I was able to exploit pretty basic parsers, it was time to try harder and aim for bigger game. The workflow I used here is to use dumb fuzzing to find crashes in these smaller, easy to exploit applications do some root cause analysis to figure out what kind of coding mistakes the programmers did and inherent weaknesses in the file format itself, and then look for similar mistakes through code review. So right here, what we have seen is the mistake where the coder actually trusted the field type byte inside the dbf file, and then used that to allocate a buffer and copy into the buffer a buffer of size field length, which is also within the dbf file. And this is the mistake I'm going to look at in different source code online. Trawling through the various open source Office applications, I came across Apache OpenOffice, which is older than 20 years and has been downloaded more than 300 million times. Now in the dtable.cxx source code file, I spotted something familiar. Here we see the data type integer switch, where it instantiates a buffer of size int32, but it copies a value of size n length. So this seemed like a variation of what I've done in the previous vulnerability, where it trusts the user provided field length, but also copies it into a buffer of size field type. So even though it's not the exact same bug, the coding error has the same faulty logic that might lead to a buffer overflow. Using my proof of concept from the previous vulnerability, I quickly generated a new file and opened it in Apache OpenOffice spreadsheet application. And indeed, I got a crash. However, this time, even though I did override the SEH, it was not able to execute any code due to a protection called Safe Exception Handlers, which prevents this kind of thing. There are also other various memory protections that will compile with the binary, such as address space layout randomization and data execution prevention. So these protections would have to be bypassed by my exploit. Additionally, I had to pass an inline validation check in order to reach the vulnerable code. So what you see here on the left is some of the assembly code, and the compare EDI EAX instruction is the comparison check. If it fails this check, it would actually trigger the exception, and the exploit will fail because of the safe SEH protections that I mentioned earlier, even though I've overwritten it. So I resolved this by ensuring that the corresponding bytes in my payload using dynamic analysis and WinDBG was set to the expected value, which is 1. And I got this offset, just by checking and comparing the various bytes with the memory at that time, in this case, EDI and EAX. After passing the inline check, it was time to try to bypass the DEP and ASLR memory protections. And one of the easiest way to do this is actually just to latch on to any of the imported modules by the binary and use one of them that is not compiled with any of these protections. In this case, I enumerated all of them using the gnarly WinDBG extension, and this pointed me to libxml2, which was indeed not compiled with ASLR or DEP protections. So I could use this library as the starting point for a return-oriented programming chain, or ROP chain, in order to bypass DEP eventually. So if you're not familiar with ROP chains, I'm not going to go into too much detail here, but essentially it's a technique that uses gadgets from a different library or another part of the code, and it calls those instructions and keeps returning to itself and calling more of those gadgets again and again until you finally do what you need to do in memory. In this case, you might want to pop a calculator, you might want to load another library, you might call a function from those libraries, and so on, depending on what you want to do. So what I had, based on my override, was an overwritten return pointer, which is the starting point for any ROP chain. But I soon realized I had a big problem. It was limited to 256 bytes. So no matter how much I set field length to, the program would only copy about 256 bytes at a time. This limited the amount of chains I could use, the amount of gadgets I could use, and this actually kind of discounts a lot of the traditional ROP chains. And in this case, my plan was to use get module handle, get proc address, and finally virtual protect to remove the memory protections. But this is not possible if you only have a certain number of bytes. So my next option, after trying different optimizations in the ROP chain, was to simply run get module handle, get proc address, and then locate the winexec functions, which takes in a shell command argument, and which will then execute as per normal. So I did do this and was able to actually just pop my own calculator using this chain. And for simplicity, I built the POC in x86, but it's also obviously exploitable and executable as well at that time. There we have it, CVE 2021-33035, which is a buffer overflow via a DBF file, which overrides a return pointer with a DEP and ASLR bypass to finally execute arbitrary commands by the attacker. So I'm going to play the POC right now. And this is just to prove that it's on Windows, the latest, most updated Windows, the most updated Apache OpenOffice. And we're checking the version here. I'm now going to open the payload. And this is going to cause a crash after opening it with the dialog, and it's going to pop calculator. So what I'm showing here is also to prove that calculator was coming from the OpenOffice process itself, proving that it was indeed arbitrary code execution. So this is kind of the proof of concept that we have for Apache OpenOffice right now. After the exciting part of finding and exploiting vulnerabilities, you get to the slower pace of vulnerability research, which is disclosure. And this can take months instead of days, especially if you're trying to be more responsible with your disclosure. Because in bug bounty, they have something called service level agreements, which specify how long maybe the triager or the vendor are supposed to get back to you. But in the vulnerability research space, this can vary greatly between different vendors. They have a different timeline. They have to review the patch, prepare a release, and then release it in stages if it's a really popular program, such as Apache OpenOffice. So for Apache OpenOffice, this took several months, and you can see the different timelines here, what I had to do in order to get the patch. At the time of recording, Apache OpenOffice has released a patch test installer, as well as patched the source code on GitHub. So you can see on the left, the kind of changes they have made, and essentially it does a memory length check this time in order to prevent the same buffer overflow. After finding initial success with dumb fuzzing and code review, it was time to move on to more advanced techniques such as coverage-guided fuzzing, as well as in-depth reverse engineering. So what we've covered today is really two aspects of vulnerability research, which is dumb fuzzing as well as code review. However, if you want to move on, I'm going to post more about that in our Medium blog at csg-govtech, which I do recommend for you to learn more about latest disclosures as well as in-depth blog posts in the future. Today, I will publish the first of a two-part series covering DBF-related vulnerabilities. The first part goes into more technical detail behind this talk, including root cause analysis. The second part will be published in a week or two and discuss how I used coverage-based fuzzing to discover a remote code execution bug in Microsoft Office. I hope they will be useful to those interested in starting out in vulnerability research, so do check them out. Now, before rounding off today's talk, I'd like to give a shout out to GovTech's new Vulnerability Rewards program on HackerOne. It's a year-round program that offers up to 5,000 in its typical bounty table, but also offers a special bounty of up to $150,000 for extremely critical vulnerabilities. So do check it out on HackerOne if you have time. So there are a few requirements and steps you have to take to join the program, as you can see here, and you can just check it out on the HackerOne page as well. So I don't work on the program myself, but I do look forward to more hackers joining in and contributing vulnerabilities to the GovTech VRP. And that's it for today's talk. Thank you so much for your time. If you have any questions, there's going to be a Q&A on Discord later. I have the same username as Space Raccoon, and I look forward to your questions. Have a great day.